So in this recording, we will continue discussing the one-dimension steady convection diffusion problems. We started that in the last recording when we introduced the general transport equation, and we were able to simplify that equation to end up with a new formulation that's count for the convection term. So let me recall what we did quickly last time. We started from the general transport equation. Then we simplified this equation a little bit until we go further and add more terms to it. So we started with the steady flow. So that's going to be 0. And you can count for the presence of the source term or not. That's fine. So we end up having this equation here. The next step after you simplify the general transport equation is to integrate that equation over the cell volume. So I'm going to integrate over the control volume for nabla rho pi v equal the integration over the control volume of nabla dot kappa nabla phi plus the integration over the control volume for the source term. And this is dv, and this is dv, and this is dv. We integrate over the volume of the cell. Then we use the divergent theorem to convert each integration over the control volume to integration over the control surface by replacing this by the flux. So that's integration over the control surface of the rho phi. And since we are doing one dimension, so the vector v, the velocity vector will be only actually u. And this is totally dot dA. This should equal to the summation over the control surface of kappa nabla phi. Nabla phi also is going to be one dimension, so I will write it down as d phi by dx. Right, and this is totally dot dA plus. We have two options for the heat source. We either replace that by an average volumetric value times delta V, or the linear relationship, which is given by SU plus SP times phi. So we have this option, or we have this option, depending on the given information in the problem. That term is different. Let's put actually the SU plus SP times phi. Okay. Then we needed to simplify this, right? This is over the control surface, so that's has to come twice, one for the east, one for the west, right? So then we introduce a new term. Let me break it down here. So if I have the central point P and the central point east and central point west, and these are the faces of the cell. So this is the east and this is the west face here. So we can actually break down that into the east and west face, and this term for the east and west face. So I can end up having like rho times u, and we know that dA, right, as a vector, it's going to be n dot dA. That's the normal vector here, and the normal vector is always going outward, right? So that's why it makes the east face is positive, and making the west face is always negative. So this is going to be rho UA to the east, phi east. I'm just recapping what we did in the previous one, minus rho UA to the west multiplied by phi to the west equal to kappa times A. This is east, east, d phi by dx on the east, plus minus kappa west, A west, d phi by dx on the west, plus the source term added to it. Then we were looking to approximate a few things here. Number one, we call the multiplication of rho UA, which is simply the mass flow rate. This is indirectly, that's your mass flow rate. We call that F So it's rho u times A. And the keep in mind that A is delta y times 1. So this is going to be A is delta y times 1. 1 is the depth. So I can get that. Then we introduce a term that's D. It's kappa A over delta. That's the equation. Still A here is delta y times A. So these are the two new terms that we introduced here. Then the issue was actually how to approximate phi at the east face, phi at the west face, and the gradient of phi on the east face and the gradient of phi on the west face, right? So we're looking for all this information at the face. If I substitute here, I'm going to get f east, phi east, minus f west, phi west, equal to kappa east. I would keep it that way till now. D phi by dx on the east minus kappa west, a west, d phi by dx at the west. And I'm going to add the source term in the form of the linear function. So that's the ending equation here. And each one of these f and w is presented here. Again, for simplicity, when you choose that delta x east, and this is delta x west, if you choose these are the same, so you get delta is the same. Thermal diffusion coefficient kappa, which in heat transfer is going to be the thermal conductivity. If it is the same, so this will be the same. The area is not going to change. You can actually have if the D is the same, east or west. And again, we talked about F, that's the mass flow rate. And we said that for mass conservation, if that's your cell, whatever the mass flow rate that's coming in should equal the mass flow rate that's going out. That's a mass conservation because we are solving steady state so far, right? Which means that you can end up having one value for F, either it's the east face or the west face one. You can have one value for D, either it's coming in the east or the west. So you have to do a little bit of smart way of discretizing your domain to simplify things. You don't want to have F east and F west as a value. It's different. So you can eliminate a lot of complexity in your math when you choose wisely the dimensions that make your coefficients very close or similar. So again, the challenge was how to find the value of phi at the east face, the value of phi at the west face, the gradient of phi relative to the x on the east face, and this also in the west face. So we're looking for the values on the east and west face of the cell. We know the values at the nodes. This is what we know, but we don't know the value at the faces. So that's what the finite volume is trying to do, simplifying anything on the face by the known node values. So for the diffusion term, which we covered many times before, let's actually keep that here and let's actually draw again. There is the P, there is E, and there is W. These are the three different cells, right? What we do, we always assume linear variation of the phi between the cells. So I'm gonna have line here, and if I do projection, that should be phi E capital, and this is the phi west capital, and this value should give me phi P capital, and now that should be the phi on the east face, and this should be phi on the west face. So I need to find these values here and the slope of the line by known node values here. So the for the diffusion term, we did approximate d phi by dx on the east face. We want to get the slope of the line on that east face. That's the east face. This is the west face. So okay, the slope of that line at the east face can be actually taken by the slope using these 2 points here. So this will be phi E minus phi P divided by the distance here, which is delta x east. And let's mark this distance here, delta x west. So it's phi east minus phi P divided by the distance in between. This will give us the slope of the line at the east face. In a similar way, d phi by dx on the west face can be approximated by the slope of the line using these two node values and the distance in between. So it's going to be phi p minus phi west divided by the distance delta x west. So this is not new. We did a lot of diffusion problems, and this is the approximation that we get. And again, this is central differencing scheme as well. That's obvious here. Now, the approximation for phi east and phi west, this is what we started last time, and we used what we call it also central differencing scheme. So here we have central differencing, and we also apply central differencing scheme. ING. Okay, so how to do that? It is simply the average. So what I'm going to do, I will assume the value at the east face is simply the average between phi east plus phi p divided by 2. And the value of phi on the west face is an average value of the two values of phi at the surrounding nodes here. So this will be phi p plus phi west divided by 2. Okay. Let's call the distance between the P and E here, which is delta x e, right? This is what we call delta x e. Let me call that for simplicity. I'm going to call that distance here b small. I'm going to call that distance here a small. So, or delta x e, delta x west, it doesn't matter. You can call it the same way. So, in more generalized form, if you want to get the value of phi at any face, so general definition of phi at any face. What is the general definition? Phi at any face can be calculated by psi times phi of the east plus 1 minus psi p, whereas psi is equal to a over a plus b. Or you can say it's delta x west divided by delta x west plus delta x east. Okay. And if I want to use A and B as well, I can actually define d phi by dx on the east face could be phi east minus phi p, and simply I can call that A, or that's actually B, and d phi by dx on the west face is simply phi p minus phi west divided by A, right? It's just a different way of presenting it, but let's look to this equation here. In our case, we pick delta x east, which we call it B, and delta x west, which we call it A, is equal. So what's the value of psi? In case A is equal B, or delta x east equal delta x west, the value of psi will be simply A over A plus A, or is going to be delta x west divided by delta x west plus delta x west. So you end up having what? You end up having half. So let's put psi equal half in here. So phi at the face is equal to, psi will be half, so it will be half of phi east plus 1 minus half, it will give me half phi p. So I'm going to end up having phi east plus phi p divided by 2, which means that this approximation that we used here, it is only defined when you are choosing these distances are equal. if these distances are not equal, if they are not equal, you have to calculate the value of psi based on these distances. Okay, so if your grid is not equal, if your grid is stretched somewhere, let's assume that you have a solid bar and you decided to have this cells like this. This is a smaller cell, a little bit bigger, maybe these are equal. So when you deal with these 2 points here, now you will not get, let's assume that we have a smaller one here too. So if this is your P, this is your east, this is your west, now these distances are not the same. I'm not worried about this in the diffusion term because we put everyone with its own value here, right? Delta X east and delta X west, each one has its own value, right? But this is an assumption assuming that delta X east and delta X west are the same. If not, if delta X east and delta X west, like this case here, they are not the same, the effect of the east node and the west node is different. They have weighted effect, right? And this is what we call the psi. This is the weight effect. So be careful. If these distances are not the same, you cannot use divided by 2, the simple average here. You have to calculate psi, and this will give you exactly how to approximate phi for the diffusion term on each phase based on these values of A and B, or these values of delta X east and delta X west. So this is very important. Keep that in mind. Okay? But so far, all the problems that we are dealing with, we are assuming delta X east, delta X west, or A and B are the same. If they are not the same, you cannot use this. This is a special case, right? When they are equal, it ends up to have psi equal half, and the definition in the general definition here end up to match this. So please keep that in mind when you are dealing with the convection diffusion problem. So far, and then we went through an example, right? We had a float flow problem. We have a one-dimension domain, starting with the boundary condition that phi is equal 1, and phi at the end B is equal 0. Then there was a velocity going here, and we did divided that domain into 5 equal cells, 2, 3, 4, 5. We defined the nodes 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Rho was given by 1 kilogram per meter cube. Also, we did half kappa is equal 0.1 kilogram per meter second, and we got A is equal 1. I'm just recapping what we did before. The total length of the domain is 1 meter, and we did solve 2 cases in this problem when the U is equal 0.1, and number 2 when U is equal 2.5. Right? And we were able to see that the analytical solution as well was given that phi at any location x minus phi at x equals 0 divided by phi at x equal L minus phi at x equals 0. It's equal to E to the rho U x over L minus 1 divided by E rho U, sorry, that's per kappa. And this is L over kappa minus 1. We did solve the 2 cases. In the first one, we were able to see that the analytical solution, this is phi, this is x. We saw that the analytical solution was coming like this. Then the numerical solution was really matching nicely, right? And the second one, when we did the solution, we noticed that analytical solution was, it was going like this, but we noticed that the numerical solution was diverging, right? We got weird values. And the reason we didn't have a conversion solution was actually the Bickley number, the cell Bickley number. We did apply 2 things for the stability of the solution. Number 1 is Scarborough criteria, which is simply summation of the absolute values of the neighbor cells coefficient divided by the absolute value of AP. Has to be less than or equal 1, with at least 1 node has the inequality less than 1. The second stability criteria that we did apply last time as well is a Sill Pickley, which is F over D should be less than 2. What happened in the first case, both Scarborough criteria and Sill Pickley number was satisfied. But when we look to the second case here, Sill Pickley number was much more than 2. If I recall correctly, it was like 5. And we have to readjust the dimension of the cell because if you substitute for F is rho UA, right? Rho UA divided by kappa A over delta. That should be less than 2. A will cancel out. I will have rho U delta over kappa has to be less than 2. So rho is probability. Velocity was given by 2.5 in the case number 2. Then kappa was given as well. Then I was able to calculate the delta to ensure that your Pickley number, Sill Pickley number is less than 2. And we discovered that delta has to be very small to the limit that we have to divide this into 20 cells. And when you solve the problem with 20 cells, you will get really a very converging solution. And I had shown you guys a plot of the results. Okay. So this is a summary of the central differencing scheme for diffusion and convection problem here. So central difference scheme is great when you do convection, diffusion, convection when you have a small Pickley number. So these are the characteristics or the advantage of using central differencing method. Number one, it's good for diffusion, convection problems with small Pickley number, which is very small value. So that's the advantage of it, okay? And in the central differencing scheme, as we mentioned, it's assumed linear variation of the value of phi within the cell, okay? But this happened when the Pickley number was very small. Then number two, it's unstable. This is the disadvantage, unstable when we have large Pickley number. So if you have your Pickley number greater, could be like 5 or 10, you cannot use actually 10 or 15, something like that. It's not really working fine for these problems. So we have to find more stable solution or a scheme that can cover a wider range of Pickley numbers. So we don't have that problem when we solve large Pickley number cells problem. Okay. Again, a large Pickley number, it will give you the chance to play with these parameters here to adjust your value less than 2. But if you are going more than 2, it's gonna be unstable, and you have to find a different scheme. And the new scheme that I'm interested to introduce today is called the upwind differencing scheme. So let's start looking for that new scheme here. So this will be the upwind differencing scheme. Remember, all what we need to do is to find an approximation for the value at the cell face using the known values of the central point of each cell. So if I have the 3 neighbor cells, this is P, this is the east, and this is the west. Right? This is the east face, this is the west face. How to find the value of phi or the gradient of phi on the face, on both faces using the data at the central. So let's look into that scheme and how to solve the problem. So again, the general equation that we need to solve is F east phi east minus F west phi west equal to kappa east A east d phi by dx on the east face minus kappa west A west d phi by dx on the west face, and you may or may not have the source term. Again, we don't need anything from the source term. The approximation is known. It's always linear. Don't change that. So the question is, these are all calculated at the faces of the cells, and that's what we need to approximate. Okay, so let's look to the diffusion is not going to change. We will not change the diffusion thing. So we will have linear change for the phi. So d phi by dx on the east, it's equal to phi east minus phi p divided by delta x east, and d phi by dx on the west face will be phi p minus phi west divided by delta x west. Again, we have that linear change. That's for the diffusion term, right? So this is phi east, this is phi west, right? And this is phi p. So the slope at the face here can be calculated by the difference here and that divided by the delta x east and delta x west. Nothing changed with the diffusion. So we're going to stick to the central differencing scheme for diffusion. So for diffusion, we're still using the central differencing scheme. What we need to look for is a different scheme than the central differencing one for the diffusion, for the convection term. Okay, so how we can approximate the value of phi at the east face and the west face? Let me actually draw the domain again. That's central point P, that's E, that's W, and here is the west face, and here is the east face. Okay, so I'm looking for the value of phi here, phi on the east face. I'm looking for the value of phi here, phi on the west face. Okay. So to pick the value of phi, it's going to depend actually in the flow direction. And this is one of the major differences between the upwind differencing scheme and the central difference scheme. Central differencing scheme is taking average, right? So it doesn't tell you exactly where the flow direction is, right? You take, again, let's recap this. The approximation here, either it's divided by 2 or there is a different weighting factor here. It's an average value, right? Could be 1/3, could be 1/4, whatever it is. But it doesn't actually tell nothing here in this information. It's telling you what is the flow direction. It's going this way or it's coming this way, right? Diffusion, we have used diffusion. It's not related to the flow direction, but the convection is the one supposed to tell you what's your flow direction in this. You cannot tell when you use the central difference scheme. The upwind differencing scheme actually can tell you the flow direction. How? That's what we're going to explain in a second here. So this is the domain. Let me just highlight this. So let's assume that we have the flow going into that direction, and we will give that positive flow direction, and this will be the negative flow direction. So in the upwind scheme, the value of phi at the face is taken to equal the value of phi of the upstream node. That's how we pick the value of phi on the face. Again, I'm looking for phi east and phi west, which mean the following. If the flow is going positive, the flow is going this way, this value here, the point P would be an upstream node to the face east, right? So this is actually phi P, We usually do it that way. If the flow is going this way, I will pick up for positive flow. The value of phi of the east face will be picked to be the upstream node value. So this is the upstream, this is the downstream. If the flow going this way, if the flow is going this way, this is called upstream, this is called downstream. If the flow is going this way, which we call it negative, this is the upstream, this is the downstream. So let's look to the positive flow here. If the flow is going this way, I will pick the east value of phi, the value of phi on the east face equal the upstream node value. So phi east is equal phi p. The same here, if the flow is going this direction, I will pick the value of phi west face is the same as the phi on the upstream node, which is phi w. So this is the approximation that we will do for the positive. What about for negative flow? Let's do that in a separate piece of paper. So let's keep that side by side so we can see the difference. So I have the domain is here. That's node P, that's node E, and that's node W. Let's indicate the location of the faces. That's that west face. This is the east face, right? Now I'm looking for phi east and phi west. And the flow is coming this way, right? If the flow is coming this way, the node E is presenting the upstream node for the east face. So for negative flow, in this case, phi east will equal phi E capital. Now, if I want to get the value of the west face and the flow is coming this way, the node P will present the upstream node for the face west, which means that phi west, which I'm looking for, is equal phi P. So from this approximation, if you look to these two approximations, you can actually tell what is the flow direction, which was missing in the central differencing scheme solution. So that's one advantage that we got from the upwind scheme. So number one, you can tell the flow direction from the approximation here, because you can determine what is the wind, upwind or the upstream node of the east face, so you can tell which flow direction is. So if you find that phi east is equal phi p, it's telling me that I have a positive flow direction. If phi east is equal phi e capital, this is telling me I'm going into the negative flow direction. So that's one of the advantage here. But you see that the variation is linear, right? So it's not linear, it's constant actually. So the upwind scheme here is not changing linearly like that diffusion term, right? It's not doing that. It's assuming that phi has constant value within the cell, right? So phi east is equal phi e small, and phi p is equal phi w, or in this case, this is phi west capital is equal phi west small, phi p is equal phi e. So it's assuming that phi it's always constant within the cell. And again, this scheme is really very stable for high Piclet number. So this is actually give us stable solution for large cell Piclet number. So these are the advantage of the upwind scheme to use when you are actually discretizing the finite volume equation for convection diffusion problem. I hope that the scheme it's very simple, and we can simply now substitute into the equation. So if we go back to the general equation, I have F east phi east minus F west phi west is equal to kappa east A east d phi by dx on the east face minus kappa west A west d phi by d west. So if you are doing a positive flow, you can replace phi east equal phi p and the phi west equal phi w. That's for the positive flow. If you are doing negative flow, you can do phi east is equal phi capital east and the phi west is equal phi p. Then d phi by dx on the east face, always it's phi east minus phi p divided by delta x east, and d phi by dx on the west face is equal phi p minus phi west divided by delta x west. So you can substitute into the equation and you can actually do simplification. So let's assume that we are doing the positive flow direction, just to pick one of the cases, and a second case should be typical. So let's assume that we are dealing with the positive flow thing here. So what I'm going to have, I will have f east, and phi east will be replaced by phi p minus f west. Phi west would be replaced by phi capital W. It's equal to kappa east A east. I would replace that gradient by this term. So I would have D east, which is kappa A over delta X east, multiplied by phi capital east minus phi P, minus I would have D west multiplied by phi P minus phi west. And you could have a source term or not, depending on the problem here. So let's collect the terms and see how things looks like here. So if I collect the term, I have phi p here, I have phi p here, I have phi p here. So what we're gonna get? We're gonna get f east, right? I will have d east. It's gonna be negative here. It's gonna come to be positive. I will have d west. This is totally multiplied by phi p. It's equal to, I will have d east, phi east. I will have d west, phi west, it's positive. And do we have anything else? I think we finished all the terms here, right? No, there should be a term here. So this should be actually d west plus f west multiplied by phi west. Okay, so let's get a new piece of paper here so I can write down the following here. I can write down, get the red pen. So this is actually, I can call that A east, the coefficient. I'm going to call that A west. So I can write down here A east, phi east, plus A west, phi west. And on side note, I know that my A east will be D east. I will have my A west equal to D west plus F west, right? Now, let's look to that term here. I can see A east, but this is F west plus D west. This is F east plus D west. I know you may have F east and the F west are the same, but this is not generalized. This is a special case, right? But we are trying to develop the equation for the more general solution here. So which means that I'm going to add F west and subtract F west. So now I can combine these two terms and call them A west. So I will have F east plus A east plus A west minus F west. That's totally multiplied by phi p. Let's actually collect the terms. So it's E east plus A west plus F east minus F west. Phi p is equal A east phi east plus A west phi west. Right? So what is this? This is my minus SP, and this is totally is my AP. So I can write the equation as AP phi p is equal A east phi east plus A west phi west. Let's continue the definition of the term. SP is equal to minus F east minus F west, right? And the AP is equal A east plus A west plus FE minus F west. That's a definition of these terms here. Again, if we are solving steady state for steady state, M dot in equal M dot out, which means that F east is equal F west. So this term will actually cancel out. So I have SP is equal 0, and I will have AP equal A east plus A west. Remember, each one of these D is kappa A over delta, and the F is rho U times A. Just keep that in mind. This is how you apply the upwind upwind differencing scheme into the finite volume problem, and to give you two advantages. Number one, you can predict the flow direction. Number two, it gives you a stable solution when you actually do a large cell Berkeley number. I hope that's conclude that section here, and all what we need to do next is actually to pick up an example and apply the upwind scheme, differencing scheme into that problem.